so this is class number 6. This is the beginning of part 3, which is all about connectivity. So let's actually get started and dig right in. First of all, what can you expect as part of this particular section? We're going to be discussing connection options using a couple of different protocols. There are lots of ways to connect a set of devices at the edge, and there are lots of ways to connect edge devices into the cloud. We're just going to discuss 3 styles or 3 types of connections that are relevant, and we're only going to discuss 2 protocols, one for each of method 1 and method 2, and then we'll talk about how method 2 and method 3 are very much related to one another. So let's actually unpack that right now. Method number 1 is a pub-sub type of mechanism. The CDA and the GDA will publish messages into a broker, a central broker or server, if you will, using topics. And they can subscribe to topics as well to receive updates from the other device. Method number 2 and 3 are based on a request response paradigm. This is a peer-to-peer model, and it may seem like, well, so is pub-sub, right? Well, yeah, it is, but we're not dealing with a centralized broker. We're dealing with a server that, yeah, it can handle multiple client connections simultaneously, but it really is all about that initial interaction between a client and the server. So if the client says, hey, I want to request a resource to the server says, okay. If it can handle it, it will do so, and it will return a response either immediately or asynchronously at a later time, but it is unrelated to all the connections that may be separate, or rather all the other connections from other clients to that server. Now, they may all be requesting the same resource, and that's fine. Much like with pub-sub, where a publisher will publish a message to a topic and subscribers will be notified about that. So it's a very different paradigm than request response, where in a pub-sub mechanism, one client is publishing messages, other clients are subscribing to a topic that will be receiving those messages, and a request response is all about that interaction between the client and the server. So let's actually talk about how we'll handle this. You can kind of choose which method you're going to use, sort of. You actually have to do both, and in Chapter 6 and 7, or Lab Modules 6 and 7, as you recall, you're implementing your clients in both Java and in Python for the CDA and the GDA. Lab Modules 8 and 9 focus on request response and allow you to choose whether your server will be hosted by the CDA or the GDA, and then vice versa for your client. Lab Module 10 focuses on both, but again, you can choose how you're going to solve for those problems and so forth. So let's dig into these a little bit more. If everything goes well with your Lab Modules 6 through 9, then most of the effort that you'll be implementing for Lab Module 10, most, not all, will be in the Device Data Manager. However, there is the encryption functionality that we talk about specifically for the MQTT protocol, which is next. So before we get into MQTT, however, let's talk about some other characteristics and actually walk through all of the designs that we've had to date. Ready? Here we go. Okay. Remember Lab Module number 1. Before we get to Lab Module number 1, this is the end state design for your CDA. There's a lot of stuff here, but you're already at this point now with the stuff that we've covered in class. However, your implementation is probably lagging a bit because you haven't submitted all the lab modules yet. What you will end up with is something that looks like this, and for the GDA, something that looks like this. Now, for your semester project, you may choose to implement cloud service functions or a serverless type of infrastructure that allows you to basically have custom processing in the cloud. It is not necessary. It is an option for you. And if you do so, it may look something similar to what you see right here on the screen. Let's look at a couple of use cases before we get into some of these protocols and whatnot, because I think this is going to be really helpful for you as you think about your semester project. In a very basic home monitoring situation, notice that we've got a bunch of sensors. We have a passive infrared sensor down here at the bottom. We have HVAC actuator, we have temperature sensor, we have humidity sensor, and we have a couple of constrained devices. And these devices are handling the interaction with the sensors and or actuator. In this particular example, and this is just a notional example, meaning it's not like dictating anything for you, it's literally saying here's a way of doing things. The CDA, there are two of them, talk to the gateway device app using constrained application protocol, which I'll talk about shortly. And then the gateway device uses MQTT to communicate to the cloud service, specifically to an MQTT broker hosted in the cloud. Notice that there's a bunch of other stuff in here too, which we've actually talked about in class, but it looks like there's actually a lot more functionality on the cloud side, and technically speaking, there is. However, the work you have to do is much more limited because you're building these applications on the left-hand side in the edge tier, and yet in the cloud tier, most of the infrastructure has already been built for you by the cloud service provider. So you're literally just, in some cases, adding some drag and drop functionality. You're typing in a rule that might be SQL based, and then you might be implementing a function in Python or Java or Go or JavaScript or whatnot. And that function is literally, well, a function, and it gets hosted within a cloud environment and so forth. So even though it looks like there's more stuff, the work that you would have to do is actually much smaller in the cloud, typically speaking. Here's another example. This one here, we are looking at monitoring a garden. Now I've got a little flower down at the bottom here, and what's happening is we've got this water reservoir and a valve that can enable that or disable it. Basically, it turns the valve, opens the valve, or closes the valve based on the actuator event sent from the gateway device, which is probably sent from cloud service under certain circumstances. All the way down, again, using constrained application protocol to communicate between our edge devices, and MQTT to communicate between our gateway and the cloud services. Now, there's a bunch of stuff that are in that I've included in here on the cloud side, which basically gives an example of how I might use a phone, for instance, or a website or whatever, to actually trigger manually an actuation that would water my plants. And so that actuation event is way on the way on the right-hand side of the screen. And that is a way that I can actually facilitate this kind of full end-to-end connectivity paradigm. And finally, we have something called pond monitoring. This is where we're just looking at the quality of the water, a very basic measurement. We have temperature, we have pH level, and we have water flow, which is going to help us decide whether stuff is growing in the pond that shouldn't be growing in the pond. So with that being said, all we are doing in this case is literally collecting data. That's it. We're not actuating anything at all. We're just feeding data up through the constrained application protocol into our gateway device, and the gateway device is feeding that up to the cloud through MQTT, and away we go. So with that being said, notice that this is actually much more simple than our other examples. So hopefully that helps. Let's now look at the rest of the designs for the semester. The CDA, what do we have? Lab Module 1, very easy, straightforward. Lab Module 2, Lab Module 1 UML, right? Again, very straightforward. This is implemented for you, making minor modifications to CDA, if any at all. And then our Lab Module 2 introduces a bunch of stuff, which now is adding a lot more functionality. Lab Module 3 expands that dramatically, includes our simulated sensors and actuators. Notice that the UML is much more involved now than it was for Lab Module 2. Things start to get even more interesting with Lab Module 4, where we have the emulator that we're adding in. It looks similar to the simulator functionality, but there's more stuff going on. Notice that we're adding 3 emulated sensor tasks and actually 3 emulated actuator tasks, including an LED emulator. Lab Module 5 actually makes things much simpler for the CDA because we did all the hard work in Lab Modules 3 and 4, and we're just adding the data transformation functionality, which we'll need in order to communicate with the gateway device app. Let's take a look at that in just a bit. But before we do that, we're going to actually focus this session on Lab Module 6, 7, 8, 9, and 10. So real quick, you're going to see a similar pattern here, where we have a connector that gives us the ability to use a particular protocol to communicate with our gateway device application. And with Lab Module 8, we have a similar thing, except we're using it as a server, which means that we have more than just a protocol connector. We actually have these things called handlers, which I'll talk about when we get to that point in this particular discussion. When we get back to Lab Module 9 or Advanced Lab Module 9, notice that the same paradigm as with MQTT introduces itself again, and this is simply using the Constraint Application Protocol, or COAP, as the client connector. And again, the pattern is identical to MQTT, just the protocol itself is changed. So with that being said, we actually have, with this, most of what we need to finish our lab modules, rather our semester project, with the exception of one piece, which is Lab Module 10. Lab Module 10 gives us the ability to add encryption to specifically to our MQTT connection, and optionally, if you choose, to implement DTLS for your Constraint Application Protocol implementation. Again, that's optional, although if you are going to use that, you absolutely should require encryption for your connections. All right, let's talk about the Gateway Device app. Again, pattern here for Lab Module 1 is nearly identical to the CDA's Lab Module 1. Lab Module 2 follows the same paradigm again. We're collecting data, except we're adding a disk utility measurement here, like how much, a disk utilization task that is going to be helpful for our Gateway Device app and not really relevant for our Constraint Device app. We skip ahead to Lab Module 5 and we introduce not just our data transformation functionality, but now all those container those container classes, actuator data, sensor data, system performance data, and something I called system state data, which is actually optional, but I include it because I like to have additional capability within my gateway device. One more quick note here, in Lab Module 5, you will be adding a persistence client adapter. I did make that optional, but it is required for the semester project. So hopefully you tackled that already. And if not, you will have to tackle it for the semester project. All right, now fast forward to Lab Module 7. We're going to skip 6 because that was focused just on the Constraint Device app. We're adding MQTT and it looks very similar to the pattern for Lab Module 6, except for the Gateway Device app this time. And then Lab Module 8, again, the pattern looks very similar as it did for our Constraint Device app when we were building a co-op server for that particular application. The resource handlers have slightly different names and they're not quite as complicated because there's actually less that they have to do, but that's for another time, and I'll get to that when we get to Lab Module 8, or rather class number 8. Okay, let's fast forward to Lab Module 9, where we're adding the co-op client connector. I've actually added a couple of observers here, and again, we'll talk about that in Lab Module 9, but it's really important that if you're going to be using your Constraint Device app as your co-op server, that you have the ability to observe resources in your Gateway Device app using the observed verb. Really, it's a special type of get, really, that's all it is, but there's a way to do that in Java that makes it super easy and efficient for you, hopefully. All right, and then we get to Lab Module 10. Notice the pattern is again the same. We're introducing the TLS encryption for MQTT and optionally DTLS for co-op, and making some tweaks to your device data manager here. Now, we also have some functionality that needs to be added for Lab Module 11. This is something called Cloud Client Connector, and this is what it looks like. Yes, the pattern is virtually the same. Notice that in this particular case, I'm suggesting that your Cloud Client Connector can inherit from MQTT Client Connector, and that is true. However, what I've suggested also is that in the instructions, you can actually have it aggregated instead of inheriting from it, and then you can implement a different interface called iCloud Client, which has a different set of constructs that would then be used to pass messages to your cloud service and maybe do some manipulation of the topic and whatnot so it fits with the cloud clients, the cloud service providers, naming convention, and then delegates the call to the publish method within MQTT Client Connector. So this UML is a kind of a simple, quick way of doing it, but there's a better way of doing it in my opinion, and that's what I talk about both in my book as well as in the online documentation. All right, so let's talk about cloud service functions for just a moment. If you choose to use a service such as AWS or Azure or GCP, you can actually go down this path here and implement your own cloud service functions, which if you're using Python, which you can do in all of those services, then you can actually pull in your data util, your actuator data, your sensor data, and your system performance data. And that provides you with the foundation for transforming the data in your cloud service function without having to rewrite that code. So that's kind of a neat way to reuse your functionality. You can do the same with Java, by the way, if you would really like to do that. All right, let's revisit the semester project real quick. Most of the changes that you'll be making in the CDA look like this. I am not going to show UML because your UML actually may differ quite a bit, but generally speaking, you're going to be making tweaks to your sensor adapter, your sensor adapter manager and its tasks, and the actuator adapter manager and its tasks. And then obviously changes to device data manager to facilitate the orchestration of messages going out and coming back in. Your gateway device application is going to mostly be just updates to your device data manager. However, there's also this new thing called SMTP client gateway, which means that you will be implementing a simple mail transport protocol, a client in your gateway device app to send a message through SMS or through SMTP. Basically, it's through SMTP, but it could be redirected to an SMS receiver, such as your cell phone. All right, and then your cloud service functions might look something like this, where you could basically be adding an actuator notification function, maybe adding some other functions and whatnot. It is completely up to you. And again, you don't have to be implementing any code in the cloud for your semester project if you choose not to do so. You can use something like UBDots, which gives you virtually code-free way of configuring your environment. So something to think about. All right, now what? What do we do now? Well, we go into MQTT, specifically version 3.1.1, because that's the version for the most part that's supported by the cloud service providers. We are at MQTT version 5.0 as of about a year and a half, or actually about 3 years ago now. But it is something that you should be aware of, certainly, but we're not going to be using it in class to keep things compatible with existing services that are available using this particular protocol. What is MQTT? Well, remember, it's a pub-sub messaging protocol created in late 90s, 1999, specifically for use in the oil and gas industry. I believe it came out of IBM. It was standardized in 2013. 3.1.1 first, of course. Well, actually 3.1 was preview to 3.1.1, and then we added 5.0 not too long ago. It's also an ISO and IEC standard. Note that you can access those at the links below. As I said before, it's client server based, with the server serving as the message broker. By spec, it works on top of TCP/IP, but you can also implement it on top of other protocols using the MQTT SN protocol, or rather specification. All right, where is it used? Well, commonly in IoT, machine-to-machine communications and messaging systems. Most IoT cloud providers, at least that I've explored, all implement an MQTT broker, and this is across a wide range of service providers. Now, for testing purposes, you'll want to install your own broker, and if you've read my book, specifically chapter 6 and the preview to part 3, then this will be old hat, and you should have already been doing all of this stuff, and there are also some test servers online as well. Okay, how does it work? We've got this diagram and that diagram that show you the connections and whatnot, and you can review this in the book as well. This is another diagram that's also in the book, but notice that every participant can be a publisher and subscriber. In fact, the broker is also a publisher and subscriber, technically speaking. What will happen is if client A wants to publish a message to topic PIOT, then it publishes it to the MQTT broker. The MQTT broker then creates, if it hasn't already, a topic for PIOT, and then another client could subscribe to that topic. And then what would happen is the broker would receive the message, it would put it into this particular queue, and then it would look at all the subscribers, and it would then publish that same message to those subscribers. Okay, so that's important to note that it is basically pub sub, et cetera, et cetera, et cetera, et cetera, et cetera. Okay, So everything being managed through the server. So when I say et cetera, I'm really talking about additional clients connecting into that server and the server managing those connections and whatnot. In MQTT, everything is a control packet. How many do we have with 3.1.1? 14, right? Well, we have 16, but 2 are reserved, so we can't use those. We can only use 14. I'll talk about those in just a minute. Control packets have up to 3 parts. The first is always fixed and always exists. This is 2 to 5 bytes in length, and the reason for the variance is because there's a size that's captured in that fixed header representing the rest of the packet, or basically the entire packet size, I should say. The second is a variable header. Most control packets have this, but not all. And then the third is a variable payload, which, by the way, would also include username and password if one is included or they are included in the particular packet. Every control packet has a type. It's a 4-bit field that represents one of these values. Basically, we're dealing with a connect, conACK, which is the acknowledgement to a connect, depending on how we're actually handling. I think that will, excuse me. This is for editing purposes. Every control packet has a type. It's a 4-bit field. And note that there are the 14 listed down below here for MQTT version 3.1.1, ranging from connect all the way down to disconnect. And the C to S and the S to C, or the C to S and the S to C provided here is literally client to server. So C means client, S means server. I think you get the rest of the point here. All of these packets will have the fixed header, and this is the breakdown. Again, you can read this in my book as well as in the spec. I highly, 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 highly recommend that you read the specification, which is linked down below. So make sure, folks, that you have the specification at the ready during the quiz. You will need to reference things in MQTT, NCOAP, and other specs. So be aware that that is coming. Let's look at the protocol in more detail. Notice you can use your protocol analyzer like Wireshark to basically retrieve the information in packet form and see exactly what's going on. In fact, for the lab modules, that was a requirement because I needed you to paste the Wireshark output specifically for the MQTT control packet in your assignments. All right, here's what a connect control packet looks like with a variable header. Notice that here's all the stuff. We've got a bunch of things broken down, including the connect flags, such as username and password, which in these cases, notice, are not set. It's a binary protocol, and these bits are not flipped on, they're flipped off. So that's why we have a 0. However, a clean session flag is set to true. And remember, a clean session means that it's the client is negotiating with the broker that it wants the broker to start fresh, even if that same client with the same client ID listed down below has previously connected. All right, publish looks like this. There's a bunch of stuff here, a little bit less because there's no connect flags. However, there is a payload. So what we have in the payload is the stuff that you see here. In fact, it even includes our topic, which is important to know. MQTT control packet flags include quality of service. We have 3 different types, specifically level 0, 1, and 2. Your cloud service provider MQTT broker connections will generally only support 2, 0, and 1, whereas your local environment will support all 3, and all 3 are needed in order to solve the problems that are presented in your lab modules. You'll also need to know all 3 for the quiz. All right, so read that and definitely follow up on that in my book, as well as, most importantly, in the specification. Clean session. This has been a common question that we've had in class. What does it mean? What does it not mean? If we set this value to 0, remember the client ID, and this generally go hand in hand, except if clean session is true, in which case it doesn't really matter that much. Clean session flag, if it's 0, however, we do need to have a client ID so that when our client, or we can get away without it, but really what's important is that we have to have a client ID set if we want to facilitate reconnects and picking up where that client left off again. So that's really what I'm getting at. That first connection, of course, it's not going to have the client ID, but again, the idea behind clean session or setting it to 0 is that your client ID needs to be set so that the server remembers what to do when you reconnect in the future, okay? So hopefully that makes sense. So wills, what are those? This is a way for a client to say, hey, if we get disconnected server through, some means of that is not me saying I want to disconnect, then this is a way for the broker to notify other clients of a particular message, a will that this client wants to broadcast or wants the server to broadcast to the rest of the clients. Other control packet flags, important to know. You can read the specs on the details. We use this to manage message state when QoS is enabled. So if we have a duplicate message that gets retransmitted, this is an important flag because if we end up getting, a duplicate, the client should know and be able to handle that accordingly. And so if this flag is set, and then I can verify that I haven't already processed that particular message if I'm the client. And a retain is used for a QoS with a QoS to determine if a message must be temporarily cached. Technically, we can set this, technically speaking, if we set this to on, the server, the broker, can choose to even retain a quality of service 0 message. It's up to the broker, and this is called out in the spec. There are a lot of rules here, so you should look at the specification to understand them fully. All right, let's move on. Whew, a lot of stuff. Okay, so when we want to connect these things together, we have to be thinking about topic names. So in MQTT, topics are just names. So what do we have when we have a topic name? It looks like a URI, like PIOT / constraint device / sensor message. Topics are hierarchical, and we'll get into this in more detail when we get to CoAP. PIOT is at the top level. It's followed by a /. That's a special character that denotes the next level in the hierarchy. So it's really important that we use that judiciously. We can technically start a topic with a /, and some service providers, as we've seen, will actually specify that. However, it is not necessarily the practice that you want to go forward with your own internal system. Just be aware that whatever naming convention you use, the names themselves in your topic have to conform to the allowed characters within the specification, and perhaps more importantly, the allowed characters within the broker implementation, which can change from implementation to implementation. My recommendation is that you leave the / off at the front because it's really easy to basically get this confused. So just come up with a standard format that is going to be consistent. Make sure that everybody knows what that is so that you don't end up like missing messages. This has happened before, certainly in my own work. And I've made this mistake with my own implementation where I forgot that I added a / and I forgot to include it with a publish and a subscribe, and things just didn't work. So with that being said, just be aware that there are some important considerations for naming topics. Wildcards are supported too. They have some limits. And also it's important to note that this can add an unnecessary processing burden on your device. If you say, for instance, in your constrained device app that you want to subscribe to everything from PIOT all the way down, and you're getting tons and tons of messages, especially those that might be destined for another device, well, now you got to handle all that stuff, and that can really be a performance problem. So my suggestion is that you use these very judiciously, very carefully, and only use wildcards when absolutely necessary. This applies in the cloud too. When you actually stand up your cloud service function rules, or rather your routing rules, I should say, for your MQTT broker in the cloud, you can actually specify a wildcard in your rule. But again, that means that you're handling every single thing, and you may want to do that, or you may want to be more specific. So again, be careful how you use wildcards. All right, we talked about this. You can review resource name enum on your own. And I think that's about it. We're going to walk very quickly through creating the MQTT Python client because you've already done this. I'd like to get to class number 7 and more importantly, class number 8 as soon as possible. So what do we have here? Remember that you've got the PAHO Python client. This is something produced by or now managed by the Eclipse Foundation. You can see the reference down below with Roger Light, who created the implementation and manages many of the code updates, or has been. So you can see the link down below. All right, network loop. We talked about this in class at length. Remember that you've got a couple of different options here for using loop to basically regularly check for network events. You can call it regularly to check for network events, or you can use the automatic async mechanism here so that loop start and loop stop would basically trigger that mechanism. They also, or rather loop start also will automatically reconnect. We have the same type of thing in Java, but a lot of this infrastructure is handled automatically, which is nice. So with that being said, here we go. All right, so callbacks. Talked about this in class as well. Remember, they're just functions that get called when something happens within your logic. That's all it is, and you can delegate all this to the infrastructure. Remember that the client ID is important. It's very, very critical that you use unique client IDs for every single one of your devices so that you don't have conflicts, because remember what we talked about before, if you have 2 clients with the same client ID and you've got the auto reconnect enabled, then as soon as the new one connects with the same client ID, the broker says, okay, I'll take that connection, and it disconnects the other one, triggering a race condition, because now that other one, which had the auto reconnect enabled, will then try to reconnect again, and the broker says, oh yeah, come on in, and it disconnects the one that just connected. And so you end up with this condition going on. And I've actually tried this experiment. It's kind of fun, but you'll see your 2 clients basically going like jockeying for position with the broker. And the broker's just like, you get one, and you get one, and you get one, and you get one. And meantime, you have the chaos, and that's not fun at all. So be aware. Client IDs should be unique for every single one of your devices. Okay, cool. So we've covered all this stuff. We've covered all this stuff. We've covered all this stuff already. So we can move now, I think, on to class number 7. And this will be very, very quick because we've already covered most of this stuff for MQTT. Now we're going to focus on the Java client. So let's actually blast ahead, get into that. So the PAHO Java client, again, this is, I think, the wrong reference. I apologize for that. This should be the Java PAHO client for the Eclipse Foundation. And you will see that, of course, in the deck that I handed out for you all. So this one also supports 3.1.1 and 5.0, though we're going to stick with 3.1.1. It has a built-in network loop to handle these TCP/IP network connection buffer drains and whatnot, and it will be managed automatically for you. But again, you have to specify your own client ID, which is right here. So you do need to specify your own client ID, explicitly set the type of persistence being used, though there is a default that will go to, I think, file if you don't set it, but I recommend that you explicitly set it here. And you can use the generate client ID to create basically a UUID every single time it's called. This clearly is not a good idea if you are enabling clean session or setting clean session to false. Why is that? It's because, well, every time your client reconnect, or every time your client application restarts, it will get a new client ID. So you probably don't want that. You want a unique but consistent client ID, if that makes any sense. So hopefully you'll be going down that path in your own implementation. All right, and this is the code, and we've talked about this quite a bit. Notice in Java, when we set callbacks, we're actually setting an interface that contains the method declarations for the callback functions, and you can implement those within the same class or in a separate class. It's up to you. Talked about this. These are the control packets once again, and here we go. Notice that encryption is talked about a little bit, but I'm going to get into that in more detail in class number 10. So let's move on to class number 8. All right, class number 8. This is all about the constrained application protocol. Let's get into it right now. Co-op messaging. First and foremost, what is co-op? Well, constrained application protocol. You can see the links to the references down below. This is the request response messaging protocol. It's been around since basically 2010 through the IETF core working group. It became a standard a few years later. And so we have our IETF RFC 7252 plus a whole bunch of other ones, including the observable spec, which is RFC 7641. You probably will want to know exactly what these RFC numbers are. Just saying. So make sure you know what these RFC numbers are. All right, cool. So it's a document transfer protocol. It's very similar to HTTP, but there clearly are some differences. First of all, it works on top of UDP/IP by spec, although people have experimented and implemented it on top of TCP. I think there's some work going on there to make that more of a formal thing, but I haven't seen it come out yet, so something you could look into on your own if you would like. Notice that it follows a kind of representational state transfer paradigm with typical verbs like get, put, post, and delete that are defined by spec, but many of the server implementations actually will define others like fetch and patch, for instance. All right, so where is it used? Well, we'll typically see it within the edge tier because it's a very lightweight protocol. And because it uses UDP by spec, generally is not friendly for traversing firewall rules unless, of course, somebody decides that they want to allow UDP packets through. That being said, there is an online resource that you can use to verify, but again, you'll need to implement your own server, which is what this particular lab module is all about. Let's talk about these RESTful calls. So we have section 581 in the spec talks about get, 582 post, 583 put, and 584 delete. Notice that we have this fancy word called idempotent, where get is safe and idempotent, and then we have the other characteristics for the other verbs. What does it mean? Operation can be applied multiple times without changing its initial response. It's a mathematical term, but we're using it here to discuss how the server is supposed to behave when any of these requests are actually made. You should know what these are. Okay, let's move on. All right, we have request and, we have response codes that look very similar to HTTP, although they're not quite exactly the same. Notice that we have a smaller number here that represents, again, this is a binary protocol, so we have a way of reflecting a number here to identify the response code in our messages, where a 2.xx is our success, 4. whatever the number is client failure, and a 5.xx is our server failure. So these are things like for 2. whatever, deleted, changed, content, etc. 4 could be like not found, like in HTTP 404. And the server failure could be things like not implemented, service unavailable, etc. You should definitely know what these are. In fact, you don't need to memorize them, but you really need to know where to find them in the specification. This is another spec that you must have available to you because, well, it's going to come up on the quiz. So be aware that that will be the case. All right, let's move on. How does it work? Well, it's kind of similar. We have a server, but we're not dealing with publish subscribe. We're dealing with request response and over UDP connection. So we initialize our UDP connection, and then we connect and disconnect. So we have our request and our response. We're done. There's also some other paradigms that we'll be looking at as well called observe, and I'll talk about that in just a little bit. So client and server communicate directly. We can have multiple clients talking to the same server or just one, doesn't really matter. The server doesn't care as long as it can scale up, and it generally for these types of requests can handle quite a few. What I have here listed is client A issuing a post, getting a response back, issuing another post, getting a response back. In my book, I talk about puts, and so that's how I chose to actually implement it. Client B is issuing a get. Notice the first time it issues the get, it gets nothing back because, well, in this particular example, that resource doesn't exist yet. Now, the way we're going to implement it is we're going to create those resources at the very beginning. So as soon as the server is up and running, the resources will exist. However, they may not have any data. So where we wouldn't necessarily respond with a not found, we may respond with a not implemented, or we may respond with like a no content or some kind of error code that indicates to the client that there's no data yet behind that resource, even though the resource itself may exist, if that makes any sense. Let's look at what an observe may look like. In this particular case, the top half is pretty much the same, but the bottom half is a little bit different. What we're going to do here is we're going to do something called an observe get with client B. Client B basically is saying to the server, hey, you know what, server? I'm really interested in resource, whatever it is. In this case, it's PIOT, constrained device, sensor message. And it tells the server that, whenever you get an update, I want you to reach out to me here, send me a message. So there's this quick negotiation. It's basically a registration of the the client's information on the server. And the server then will use UDP, which again is unreliable, although there's some characteristics in co-op that give us an ability to confirm a message and whatnot, but it will use that registration to say, all right, I know you're interested in not just one get, but perhaps multiple. So then it's effectively going to allow me to just think I realized I need to make a quick update to my book. But that being said, that's okay. What we have here is the ability to observe a resource that is updated by the server and register the information of the client to the server so that the server will then reach out to the client every time an update is made. Now, what's interesting about this is that the server will continue to run until the client says, stop notifying me. The client goes away. What happens? The server continues to run. And so what you'll see in Wireshark is the server will continue trying to reach out to the client, and the client will basically not be there to receive anything. And the server will basically get these error messages, but it will keep going. So if I'm updating a resource 10 times a minute, or maybe 100 times a minute, and I'm observing that, my client goes away, the server is going to continue doing work to try to reach out to that client. So you have to handle that in your server functionality. Writing servers is hard. There's a lot of stuff that you got to do. All right, let's move on. All of these messages use UDP datagrams. Kind of makes sense. The protocol is certainly designed for lightweight communications. There are 4 components that you should be aware of. One is very, very important. This is the fixed header. It's always required. It's always 4 bytes. You have a token, you have options, and you have payload. Token is really important. It generally is set for you by the underlying infrastructure, the library that you're using. So what does this look like? So much like an MQTT control packet, the co-op packet, the datagram, specifies how the interaction is going to unfold. That first thing is the fixed header, 4 bytes, broken down as follows. The second, again, the token, it's optional. Sometimes it's required, but generally speaking, you're going to have this generated for you on your behalf, which is pretty awesome. And then you have things like options and your payload. That payload is really important. It will go up to the maximum UDP packet size, which we've talked about in class. And if you recall, is, I believe, 64K. So you should know what this is. All right. There are 4 types. We have confirmable, we have non-confirmable, we have acknowledgement, we have reset, we even have empty, which is not really a type, but it's kind of important to call out. It's a 0.00 code, only the 4-byte header. It's not a request, it's not a response. It's just a datagram that has co-op wrapper. So confirmable is really important. We use that for reliability. It requires an acknowledgement and it requires a message ID, which is not a token. It's a little different. We have non-confirmable, where there is no acknowledgement required at all, but a message ID is, and we have the acknowledgement, which is given in return to a confirm message. It doesn't indicate whether it succeeds or fails, so a failure can still have an acknowledgement, or a succeed can. It doesn't care, it's just an ACK, that's all it is. And then reset's really neat because it basically is a super lightweight message, and it can be useful as a ping to see if the server is there. In fact, the spec even tells us that you can do that, so it's kind of cool. All right, what about these tokens and message IDs and all that stuff? They're not the same. A token is used to match the request with the response. The server uses the client-generated token to correlate this. It's best to randomly generate it because, well, there can be a man-in-the-middle type of attack, and if you're using the same token all the time, then it becomes a lot easier to manipulate. So, or the message does, the stream does. Message IDs are used for preventing duplicates and optionally for acknowledgements, as we just discussed. The server will use a client-generated token to correlate its response, of course, but the message ID will potentially be different. There's up to about, it's a 16-bit ID, and that gives us the ability to have about 250 unique messages per second between endpoints. So let's take a look at what these are. I'm actually going to just talk about options real quick. Make sure that you know where the option types are in the spec. There's an IANA listing for different option types, and the specification specifically, I believe it's section 5.4.1 and section 12.2, table 7, where you can find this information. Let's take a look at the token and message ID for just a second here. So here's a request, both confirmed and non-confirmed. Notice that the message ID for the confirmed is 17733, and for the non-confirmed is 24021. The token is this hexadecimal code, and it's different for each. Now we go back here, notice that the token is the same for each, right? But the message ID is only the same for the confirmed message. It is different for the non-confirmed message, okay? Sorry to go back and forth so quickly, but I wanted to call this out so you can see confirmed message is going to have the same message ID. The non-confirmed will not, but the tokens will be the same between them because we need that for request response matching. All right, post similar, we have message ID of 38195, and we've got the same in the confirmed and so forth. So that's what we would expect because, again, we want to match the acknowledgements. Okay, so that is it for now. Let's actually talk about creating a co-op server very quickly because you've gone through these exercises already. Remember, you can build your server in the GDA or the CDA. It's pretty lightweight, and so it actually kind of makes sense to use co-op as a server within your constrained device application. It's actually doesn't require that much processing. You can certainly run your own tests to see if this is the case. And then you can implement server-like functionality for this type of device, which is kind of cool. If you're going to go down this path, though, notice that your handlers, the way you handle gets, puts, posts, and deletes will be a little bit different between the CDA and the GDA. Because in the case where the server is hosted within the CDA basically needs to be receiving actuator events from the GDA as effectively a put, whereas the GDA can observe sensor data or system performance data. In the case where the GDA hosts our co-op server, then the CDA can observe the actuator command resource, but then use the put or frankly a post to send sensor data and system performance data. So the roles are reversed. Obviously the roles are reversed, and how you handle them needs to be a little bit different depending on whether it's the gateway device or the constrained device. All right, so we kind of went through this before, but notice that if your GDA is a server, we're going to have this particular type of use case. You can read this on your own. And if the CDA is the server, then it would actually follow a slightly different paradigm. Let's actually quickly talk about a co-op Java server, and then we're going to blaze ahead into class number 9 and then 10. So we have access to the Californium Java co-op SDK for both the server and the client in your gateway device application. And it's actually hosted or managed by the Eclipse Foundation. You can see the links down below. This is, again, a great way for you to learn about the co-op protocol and, of course, implement your own server within your gateway device application. In both cases, whether you're using Python or Java, you're going to create a server, you're going to create resource handlers, and you're going to add those handlers to the server and start it. This is what I wanted to call out. Remember that adding resource handlers means that you are creating a tree structure within your server. So you're basically telling the server that you have a top level resource, in this case called PIOT. Then you have a next level resource, which could be gateway device, constrained device, or maybe something else. And then you have a third level resource tree or hierarchy that may be, system performance message, sensor message, et cetera, potentially system performance message for both. So you end up with this tree structure. Now, what's going to happen if you tell the server that you've got this hierarchy of handlers that you created using this example I've shown you right here, and the top level one is PIOT, and then you create another hierarchy also starting with PIOT. As soon as you add that to the server is going to say, oh, okay, swap and replace. So it's going to replace all the work that you did before with the new tree hierarchy because that root name is exactly the same. So it's just like, it doesn't care. It's just going to overwrite the stuff you already did. So you have to be really careful about that. And that's one of the reasons I created an example of create resource chain, which will actually track all this stuff for you to make sure that you're not overwriting a resource name at any one of those hierarchies. So to create your handler, it's actually not that hard. You can write one in just a few lines of code. Just create a subclass of co-op resource, and generally speaking, you're going to implement, no, that's not what I wanted. You're going to implement a get implementation that would just be a few lines of code where you've seen the example already in the source code and in the online repository that I've made available for all of you. So we talked about these handlers and we talked about how this would be structured, and I thought I had an example in the code. I think I do. Okay, cool. So this is back to the handlers here. The tree hierarchy, remember, top level is very, very important. Next level down, same, et cetera, et cetera. Okay, so don't forget that. Let's talk about the handler. Here's the get that I was looking at. So notice that this is literally like 2 lines of code. So you can technically implement a get request in just a couple lines of code. You have this thing called a context. Context has all the information about the client connection that you need, as well as the request itself. And then you can use that to basically tell the client, hey, I accept your request. I accept, good. And then you can respond in kind with valid or with content or whatever it happens to be that's relevant for your particular implementation. And then of course, the data that represents your payload. Post is similar, but in this particular case, we probably respond with a created. And then of course, we've got put and delete, where you'd want to obviously respond with the appropriate response code. Remember the token and message ID for just a moment. We're not going to override any defaults. We're going to actually allow our infrastructure to generate these and manage them automatically for us. So we don't really have to worry about it, but we do need to know what they are and how they work. All right, so let's actually take a look at how we would create or generate a co-op message. Now, one thing we can do is we can obviously do this, but we're going to issue a client request. And in our case, we're going to issue a client request to a specialized resource that is actually implemented for us by just calling the discover method. And that will give us the ability to retrieve all of these that we've registered using this paradigm to our client, which is here. So when we issue this against our server that's registered all of these handlers, then if we've done everything right, then we're going to get a bunch of web links back that represent all of these resources. This is kind of cool because you can use this to inform how you're going to be issuing your calls. You can parse the name and you can make a decision about like, well, how should I handle each one of these requests? Okay, relatively straightforward. Let me blaze ahead through all of this because we've seen this already. And let's quickly talk about creating a Python server. Review all of the CDA specific requirements in Chapter 8 or Lab Module 8 online. Notice that I discussed 2 different Python co-op libraries. They are listed down below with the references included, both Co-opthon 3 and AIO Co-op. They work differently and require different skills, even though they're both written in Python. So just be aware that if you're going to be going down one path, you're going to have to go all in and commit to the way that these libraries actually work. And again, your implementation will differ quite a bit depending on which one you're going to use. But fortunately, your interface to your co-op client connector and your co-op gateway, co-op server gateway will be the same. Just some of the implementation details will be very different. Much like with Java, you create your server instance, you create your resource handlers, see the links below, and you add the resource handlers to the server, you start it up. Again, depending on which library you choose, the way that you do this is going to be a little bit different. So make sure you look at the link for the examples and whatnot, and hopefully you'll be good to go and be a happy camper with your co-op server implementation. So with that being said, I'm going to blaze ahead because we talked about all this stuff and get into chapter 9 or class number 9. So here we go, creating a co-op client. We talked a little bit about that on the GDA side, but not yet on the Python side. Okay, but before we do that, remember why we're doing all this, right? We want to have options. So lab modules 6 and 7 teach us about using a pub sub protocol. Lab modules 8 and 9 focus on request response. We are in lab module 9, and lab module 10 brings it all together so that we have a fully functioning, for our purposes, edge infrastructure. All right, let's create our co-op client. Remember that there are a number of different tools that you can use, but we're using Californium, managed by the Eclipse Foundation, as I mentioned before. There are other ways to do this, but we're going to stick with Californium. Okay, so you create the client instance. No surprise there, and it's 3 lines of code for the most part. You create your client, you set the URI, you send your request, and you're good to go. Now, generally speaking, it would be helpful to create something called a response handler, different than a resource handler. Response handler is an implementation of an interface that allows you to process the response in a unique way, or rather in a way that's specific to your particular request. So it can be a really interesting and useful way to create a class that handles the response from a particular request very specifically to that request URI. So just saying that this is one way to handle it. Otherwise, what you'll do is you'll be getting a response back to your generic request, and you'll be scratching your head in your code saying, okay, I've got a payload now, I've got a bunch of stuff in it. How do I parse it? Well, this is where, again, setting a response handler can be helpful, because you can set the response handler and map it specifically for each request type or request name, request URI, if you will. So you know if you're issuing a request to get, say, sensor data, then you know the payload should contain sensor data. You certainly will validate that, but again, provides separation of concerns, more abstraction, which can sometimes be a good thing, and that's what we're dealing with here, is the good aspects of separation of concerns and abstraction. All right, you send the request. Here are a couple of examples. Notice that it looks very, very simple. The difference here is if you're posting or putting, you're including a payload, and you should specify the media type as well. In our case, we can just use text plain, but you can also set it to JSON if you wish. Send the request, and here are some examples that don't block and some that do. So if you want, you can set, again, as we talked about, a custom response handler that you can include with a particular get. And I can have as many of these as I want. The fact that I only have one doesn't mean that I can't create 10. It just means that I've only wanted to create one for an example here. But again, you can create as many of these as you want, as you need for each request that you're issuing, if that's important to you. Okay, process a response, which you're going to get basically a callback into this function called onLoad with your response object that contains all of the necessary information, including the payload, which you can retrieve as a string by calling getResponseText. Very easy. But what about a non-confirm message? Well, that's easy too. You just have to set that flag on your client connection, but just remember that once you set it, that client connection instance is going to always use it until you change it back. So just keep that in mind. All right, that's it. Let's blaze ahead into Python. So with Python, again, we've got a bunch of different clients we can use. We're going to stick with Coopthon and AIO Co-op. Again, these are tools that are available to you. My examples here are using Coopthon 3, but again, You can use AIO co-op, and the examples in Lab Module 9 online actually will use both. So you have a choice and you have examples in both. Just remember that you're going to have to be aware of how to deal with async IO if you choose AIO co-op, and you'll have to handle the synchronous nature of co-opthon if you choose that particular library. Using helper client can save you a lot of time and energy, but again, it is optional. You can just use the client directly and then create your own requests each time. Examples here are pretty straightforward. And so again, we've gone through all of this stuff before. We don't need to review it again. Non-confirm message means that you either use a specialized method call or you can customize a request, as I alluded to a moment ago, by using the make request function. So with that being said, that's basically it. And you're probably already accustomed to doing this now, so you're good to go. All right, let's blaze ahead to the semester project. I'm actually not going to review that because this is for the quiz. So we're going to blaze ahead again to class number 10. All right. Let's talk about multi-protocol integration. We're not necessarily talking about using both at the same time, although that is certainly an option. Let's go through some of the things that are important for this part of the class, and that will be hopefully helpful for you on the quiz as well. All right, let's talk about some edge connectivity use cases. So we've been working on this for, well, 4 weeks, or in this case, 37 minutes, almost 40 minutes. So I guess 10 minutes per week or something. Okay, but anyway, what we have here are a bunch of different things that we can do to help us figure out how we're going to move forward. We really want to break it down into the what, the why, and the how. So the first is, what is it that we're trying to achieve? Let's keep it simple. This is basically the problem that we care about. Then there's a why, and this is really, what is the purpose behind this? There's always got to be a why. And I encourage you to ask that question when you're thinking about a problem that you're interested in solving. Is it really interesting? Is it rather useful? Is it going to add some value? Well, hopefully it will. And this is where you can figure that out by asking, again, these questions. Then we've got the how. This is, once we understand the what it is and the why it is, then we can start exploring how is it all going to be piecing together and stuff forth. And so this is where we can create a workflow and then start thinking about where are the different components, what are the interactions going to be, and we can basically draw a line through all of this stuff and touch on the key things that are really important to make sure that we're building the stuff that we need to solve the problem. Okay, so let's talk about our what. In our case, we want to securely pass messages from the edge tier or within the edge tier, and we want to take relevant actions automatically. There are two things that we need to do for this. We need integration tasks and we have application tasks. Our integration tasks require us to communicate, but also communicate securely. Our application tasks require us to be able to handle these different message types, but also process actuation commands so that we can basically have full end-to-end kind of interaction and whatnot. Right? So that's what we are actually achieving or trying to achieve in this particular step. So integration tests or tasks, are focused on connecting the edge tier. So what we've got in this particular case is a secure connection using either TCP/IP or UDP/IP, specifically TLS or DTLS. We're going to focus on TLS. Now we can either use MQTT or co-op, but we're going to focus on MQTT. So let's do a thought experiment for just a minute. Why would we use both, or why would we want to use one or the other? Well, consider that when we have a gateway device that needs to support multiple clients, some requiring stateful connections and others only occasionally connecting, we may have a need to support both. In the case of stateful client connections, like maybe a factory monitoring system or a control system, that's non-mobile, for instance. Well, we've got a stateful connection that gives us the ability to have messages transmitted to us whenever they're necessary and even send commands down if needed as well. Whereas a sporadic client connection might be in a mobile system where, the overhead of reconnecting or retrying over a TCP/IP network because the connection was lost if we know the connection is going to be lost on a regular basis, might be too much. Or we can just say, you know what, we're going to program that in and we're going to still use MQTT, but we're going to only connect when we know it's viable. The other option is we just use co-op, which gives us a connection-less paradigm, so only connect whenever there's a message to do so. Now, this can obviously get in the way. If we are observing a resource and we keep falling off the network, well, the server is going to continue trying to reach out to us, which may or may not be useful. So these are different paradigms that could actually justify either protocol, depending, again, on the problem that you're looking to solve. So it's something to think about. All right, performance testing. You did this as well. You implemented some performance tests to see what would be the difference between using a confirm message or a non-confirm message in co-op, or the different QoS levels that we have in MQTT. And if you've implemented this, you'll notice quite a bit of a difference between them, especially between 0 and 2 with MQTT QoSs. All right, so anyway, so that's an experiment, but it's something that you should certainly be aware of, like what are the differentials between them and why might you choose one messaging or QoS level and one type of co-op message over the other. All right, we talked about this and you have access to this. Let's focus on securing the edge tier. MQTT encryption, the spec allows for it, but doesn't specify or rather require it. So what it does is it says, yeah, you can use TLS on top of TCP. So you're good to go with that if you're going down that path. The broker clearly has to support it, as does your client. In our particular case, both do, and we're good to go. We can choose between server-only certificates or server and client certificates. We can also make sure that we understand, well, what we also need to do is review the documentation and look at the security vulnerabilities that are documented at the link below. And then, of course, make sure that you review the TLS documentation so you know how to configure your server. I talk about this online and in my book, so you can review that at your own on your own time. With Java, it's a little bit more involved, but I provide a quick, easy, simple library to load those server certs for you so that you can support the first sub-bullet here pretty easily. In Python, loading a certificate is basically one line of code. You don't even need to really call set TLS set context. As long as you're setting the TLS, calling the TLS set appropriately, you're generally good to go there. And so just review this information from my book and online. And again, you should be good to go to establish a TLS encrypted handshake between Python and your broker and Java and your broker. By the way, your Java client will probably default to TLS version 1.3, whereas your Python client will default to 1.2. They fortunately will still work talking to the broker. The broker will handle both requests. All right, this is stuff that's been covered before. Certainly, I don't think it really makes a lot of sense to go through in detail. This is one that you should definitely look at your own, on your own time. The Californium SDK provides some really great examples for using DTLS, but they're very, very involved. And it is certainly not super easy to do this. Getting your Java client and your Java server talking over a DTLS encrypted connection is certainly doable, as is connecting with Python, but it's quite a bit of work, and so that's why I'm not requiring it. You could spend a lot of time just focused on this one particular paradigm, and so again, I'd rather you just focus on getting everything working, but keeping in mind that encryption is critically important, especially in a non-experimental environment where you have full control over your servers. Okay. All right. Let's talk about what you have to do here. You've got 4 tasks for the CDA and you have 4 tasks for the GDA. There's a bunch of analysis stuff that you need to do in both, but mostly in the gateway device app to solve for class lab module 10 assignment problems. So just keep in mind that you really should be familiar with the online documentation. You should be familiar with the content that's in the book, and we should go back and review the MQTT and co-op specifications. All right, so with that being said, Let me just quickly, yeah, we don't, I'm going to cover this for just a moment, but then we're going to wrap up. So there's a kind of an interesting example doing simple motion detection using a camera. And this is using the OpenCV library. There's actually a, a text file that has all the imports that would be relevant for implementing something like this, should you choose to do so. I've actually implemented this on a Raspberry Pi Zero with two different brands of camera, both non-infrared filtered cameras. And I found it to be actually both of them to work quite well for my purposes. And so what I was doing here is processing a video stream directly on the device using OpenCV and Python, looking for diffs in the frame to frame, grab a frame, copy it, resize it to lowest resolution practical, convert it to grayscale, apply a Gaussian blur to reduce the detail, because I really want to get to the most efficient way of detecting whether there was movement in a particular pixel or not. And then I would pass that back on to identify the motion image, analyze the contours, decide if it's a diff, and then pass along. And by the way, I just got a quick announcement, a quick message here, request, and that is, does the AIO co-op library include a discovery function? And I actually can't recall if it calls one out specifically, but the good news is that you don't actually need it. It's just a GET request that uses the /.wellknown, well-known /core, I think. And you can find this in the online documentation for the assignment, as well as in the co-op specification where it talks about the different URI standards and so forth. It'll actually take you to another standard that you can look at that will actually specify what are the URI standards for well-known types of requests. And so a discovery is literally just a GET request using a special URL. That's all it is. So even if it doesn't have a dedicated method for it, you can easily create it yourself. And that's actually how I execute discovery. Even though the example I showed you before uses the discovery function, in my own code, I just send it the well-known core GET request, and good to go. All right, so let's get back to the camera detection stuff for just a moment here. Notice that I've got a couple of exemplars here. Number 1, 2, 3, and 4, where we have my hand in front. Number 1, that's my initial detection. We have a little bit of curtain flutter for number 2, which is basically my hand being withdrawn. The frame didn't pick that up. I'm not running these cameras at more than I think 15 to 18 frames per second, which is still fast enough to pick things up, but I'm moving my hand very quickly. And so the detection algorithm is basically picking up the curtain flutter, and then it picks it up again, and then a third time as well in image number 4. But in all of these cases, there's a couple of things that I can do. What I can do with the diff, with basically the green box that identifies the pixels, the part of the frame that has actually a set of different, sufficiently different pixels, is I can then use the original image and I can create that little box and say, all right, does this represent, a cat or a monkey or a car or a hand? So I can use some simple machine learning to determine whether or not I can extract a feature that is something I know, and then use that to infer whether or not, the thing that moved is something I care about. So before I pass it all the way up the chain to my cloud and all this stuff, there's actually some local stuff that I can technically do to provide some kind of basic thing. So what I'm doing to keep things as super simple as possible is just saying, is there a sufficient pixel delta from one frame to the next? And if so, then there's motion. I leave it at that. But again, you can do a lot more with it. If you have sufficient power in, say, your gateway device, you can blast the frames, all of the frames that are in part of this, up to your gateway device and let it basically infer whether there's a sufficient feature that is relevant for motion or not. And so then you can go from there. Hardware requirements, H.264 capable camera. I used Raspberry Pi camera. I actually used, like I said, 2 different cameras. and then install the CV underscore imports. And again, this is something that you may find to be useful for your semester project. Just saying, certainly an option that is available to you should you choose to go down this path.